Welcome back! For all the users who are not really into GUIs, there is the possibility also to follow the makefile flow. This flow expects user to provide a kernel file and an host one, and then to use a makefile, as the one I will show you, to perform the compilation. Let me show you how it can be used. In this folder, I have an example of makefile to compile our Smith-Waterman. Actually, this makefile is general enough to be adapted to other kernel functions too. It is just necessary to specify the host source files, headers, C flags, and L flags. The same for the kernel. And then specify the name of the executables, the name for the kernel, and then the optimizations we want to specify in our kernel function. In this example, we are telling the compiler the kernel name, to use the compute unit, just one, to use all the available memory ports, and to set the bit width of the ports to 512 bits. Finally, we specify the target device to be the Virtex 7 with just one memory port, with the DDR, and the DSA version equal to 3.0. Running the makefile is very easy. There are two parameters to specify. The first one can be emulation, build, clean or clean all, to clean all the generated files. The second is the target. It can be swemu, hwemu, or hw for system build. Let's test software emulation. We need to type make, emulation, and then specify the target to be software emulation. The makefile will invoke xocc, compile our kernel and host file, and then set the environment to start the emulation on CPU. Very easy. As you can see, SDXL here generated a profile summary with some of the information we have observed with the GUI flow too. For each simulation then, it is created a folder, and it is possible to find the executable inside another folder, called as the target device. We can run the executable from here too. We just need to call the host file with its binary file. Wait, I forgot to set the environment. Let's copy from the makefile the name of the environmental variable and run it again. Great, it worked. Very easy, right? Let's now build for the FPGA so that we can check system performance. Now that the compilation for our target device has been performed, we need to run our binaries on the FPGA device. To do so, make sure to have correctly installed the target FPGA board on your system. Once you are sure that your environment is correctly set, navigate to the binary folder. Before starting the computation, remember to source the settings.x64.sh file to set the environment for the SDXL framework, and then source the setup.sh file that is in the folder containing the DSA that you programmed on your FPGA device when you install the target architecture. At this point, we can just type /host and provide the binary file to start the execution on the FPGA. As it is observable, our kernel took roughly 328 milliseconds to execute. Let's take this value and estimate how many giga operation is actually performing. To do so, let's take the value for the number of operations and let's divide it by the execution time in seconds. After doing the math, we obtain 16 giga operations per second. Hence, we are very close to the value predicted by our roofline. We have to notice here that the roofline model provides the maximum performance achievable by our code. Hence, in order to get the full performance, we should increase the optimizations that we are performing. However, as the maximum achievable performance are very low, we will have to start by slightly changing our code, and then we will focus on increasing the level of optimizations. So, great! We have our first Smith-Waterman algorithm that is actually executing on the FPGA board. In the next lessons, we will start changing and optimizing our code.